Look closely at a bare silicon wafer, and you won't find any numbers. Modern computing is not a mathematical abstraction. It is built entirely on the manipulation of physical electrical currents. The ones and zeros of computer science are a shorthand myth. The entire digital landscape is driven by physics, specifically the highly controlled flow and restriction of voltage. To understand how a computer makes a decision, we rely on transistor-transistor logic, or TTL. In this system, a logical false, or a 0, is simply a physical state of 0 volts, tied to ground. A logical true, or a 1, is exactly positive 5 volts. To prove how this works, we are going to use a virtual lab bench to empirically verify Boolean logic against these strict physical voltage limits. We will test 3 categories of components: basic, universal, and exclusive logic gates, observing exactly how they process raw voltage. Our testing apparatus is straightforward. We will use mechanical switches to inject 5 volts or 0 volts into our circuit, route those signals through integrated circuit chips to process them, and use LEDs to confirm the final output state. By isolating these components, we can observe exactly how inert physical materials execute complex mathematical reasoning. We start with the simplest logical operation, the inverter, commonly known as a NOT gate. Its sole function is to flip an incoming signal to its exact opposite state. This schematic shows a NOT gate's internal logic. A 5-volt input turns the internal transistor on, pulling output current to ground, leaving 0 volts. Dropping the input to 0 turns the transistor off, letting 5 volts pass, lighting our LED. This lab notebook records student data. Looking at the truth and voltage tables, you see the direct mapping. An input of 5 volts reliably yields 0 volts. Moving down, the Boolean expression x equals a bar indicates this strict logical inversion. Engineers deploy NOT gates for simple logic level shifting and basic signal inversion across larger, more complex circuits. By forcing a voltage to its opposite extreme, the machine executes its first structural decision, negation. We escalate from simple negation to conditional logic with the AND gate. The operational rule here is strict. The output reaches a high 5-volt state only when all inputs are high simultaneously. This truth table maps every input combination. The rows scale by 2 to the power of n. With 2 inputs, we have 4 states, but only one yields a positive result. Below.
Namaste. Thanks for watching. Stay tuned for more.